So we have the following theorem. So assume first that we have two functions that satisfy the following inequality. So you take the derivative with respect to the time t, Laplacian, and here you have some nonlinear function of u, and assume that this is greater than the same thing for some function v. You assume that so these functions are smooth and well defined, and that at time t equals 0, u of x0 is greater than v. And you assume that x belongs to a bounded domain and that you have Neumann boundary conditions, zero flux boundary conditions for both u and v. So then you have that. So assuming that the functions are well defined for all time, which depends on the function f, but we assume that that's true, then you will have that u of x t will remain greater than v of x t. All right. So that's the theorem. So yeah, we are going to prove this theorem, which is taken. It's a specific case from a theorem in the book of Smaller. So let's go. Yeah, so basically, see, if you put everything in the same side, you can get u v t minus Laplacian u minus v plus f of u minus f of v, and this is greater than 0. So if I call this thing w, I can rewrite that w of t minus Laplacian w plus so u and v are take their value in r. F is a function from r to r, and this it's regular. It's at least C1. So I can write that I can write it like that, right? With C equals theta u plus 1 minus theta v from some theta in 0. All right, and this is, of course, now yeah, this is w actually. All right. Now, our aim is to prove that W remains non-negative. So we assume that there exists some X node, T node, such that W of X node, T node equals M, and this is negative. And I want to obtain a contradiction, right? And furthermore, I assume that this is the first time T0, so there is some point, and sometimes such that W reached the value M, and so and this is the first time, and so X0 belongs to, it can belong either to omega. Omega is an open bounded set, but it can belong also to the border of omega. So it's the first time such that xt equals M, and M, therefore it's the if imam of X and T of U X and T of W, it's W X T. And so next, there is this little transformation to do. We are going to say that W equals exponential minus kt z. No, it's not this way. It's the other way around. Sorry. It's the other way. So z equals exponential minus kt minus kt times W. So we will discuss why. We'll discuss why we need to do that in this case. We'll discuss that later. So when I do that, so next, so we have that W equals exponential kt z, and so if I rewrite the previous equation, so we know that Wt minus Laplacian W plus f prime of xi W is greater than 0. So if I replace W by exponential ktz, what do I obtain? Okay, I didn't do that computation, so that way you participate with me. So please replace here W by here in this equation, what do you obtain? So if I replace W by, sorry, so W equals, so I will get exponential KTZ, and I need to take the derivative with respect to t, minus Laplacian exponential KTZ, plus f prime of us some c, and this is exponential kt z, and this is non-negative. I just replaced w by its by exponential ktz. All right, so the only thing that's not straightforward is this derivative. So it's k exponential ktz plus exponential ktz t minus exponential kt Laplacian of z, because kt doesn't depend on x, plus exponential kt z f prime c z, and this is non-negative. So I obtain that zt, so I can multiply both sides by exponential minus kt, and I obtain that zt minus Laplacian z plus f prime c plus k times z is greater than 0. Now, so I assume that my f prime is regular enough, so this is bounded. This is bounded on my domain omega. All right. And so so not only omega, psi varies with u and v, but I assume the time is finite. So if everything is regular and well defined, this will be bounded. This is bounded. So this can be negative, but I choose k large enough such that this is positive. So we choose k such that f prime c plus k is positive. Okay, so now there's two cases. So assume that x node belongs to omega. Omega is open, right? So then what you have, so then zt at time t0 so this is the first time that I reach, so t node is the first time when I reach m. So this derivative is non-positive. Because m is the smallest number, it's an inf. So it's the first time when I reach m. So at this point, this is negative. Also, the Laplacian of z, at time x node T node. This is a minimum with respect to x. So if this is a minimum, this is non-negative. Because at x node, I have a minimum with respect to the x. So now if I look at my equation, I get zt minus Laplacian z. This is non-positive, is greater than minus f prime c plus k. This is positive, and z. But z is z at this point at t0 x0, it's m, and it's negative. Why? Because at x node, t node, it's not m, but z equals exponential minus kt node double 0 equals exponential my kt node m, and this is negative. So I obtain that something that's non-positive is greater than that something that's positive. So I have a contradiction. I have a contradiction here. This is a contradiction. Okay, so this is not possible. So it might be also possible that x node belongs to the border of omega. And in this case, the argument doesn't work. So in this case, I refer to smaller. So the idea, it's proposition 913 in the book of smaller. And the idea here, so first, we have that when I look at this thing, at x node, t node, this is negative because at x node, t node, I have a minimum, right? On the other hand, the idea that you can find on smaller or Porter and Vertinger is to introduce an auxiliary function h and look at z plus epsilon h. So h needs to be constructed in such a way that this function attains also this minimum only at x node, t node. So when I will look at the normal derivative of this function, let's call it L. So if I look at this thing, it will be also non-positive. But then you can also say that equals that. And if your function is well chosen, I refer to the book of Smaller, you can compute explicitly that. This is given. This is a real explicitly given function, and the computation so this is you know that this is negative. So you will get, so you need to choose that. Yeah, so this is negative. So let's so I repeat. So on one hand, this is non-positive. Okay, so this gives you that is less than minus epsilon h n. But this is also non-positive because I have a minimum at z. So the contradiction comes if so, I need that to be is less than that. No. So what we get? So now the function h. Assume that so the function h needs to be chosen in such a way that this quantity is strictly positive. Is positive. You can do that. So I refer to Smaller, and h is computed explicitly. So next, what do you get? So from here, you get that is less than that. And so you get that this is negative. But our assumption is what? Is that you have zero flux boundary Neumann conditions. So by construction, this is zero. So you get a contradiction here. So as a project, it's one project among others. What you can do is study maximum principles in chapter 8 and chapter 9 of Smaller. So the goal here in this project is really to understand what's going on. Take your time, look at the details, and try to grab an understanding of what's going on. Yeah, these things are studied a lot. All right, so the next chapter deals with bifurcation phenomenon in reaction diffusion systems, so RD systems. And so to start with, so it's more, we start with around during bifurcation. So we consider first a simple linear ODE. So there's no space here. And I ask you first to so what is the nature and of the stationary point 0, 0? So if I consider this ODE, this linear ODE with two variables, so a straightforward computation gives you the two endgame values, which are complex with negative real parts. So the stationary point 0, 0 is a stable focus. So now I take the same system, U minus V, Vt equals 3U minus 2V. And I add some diffusion in it. So here, so I work here in one space dimension. So here I take the second derivative with respect to the x. This is a sigma. It's not 6, it's sigma. And here I add the second derivative of v with respect to x. So my space domain is just the real interval 0, 1, and with here 0 flux boundary conditions ux of 0t equals ux of 1t equals 0. And here sigma is a parameter which is greater than 1. All right. So the idea now is to start to looking at this PDE and we try to do a qualitative analysis. So I propose you to do it as an exercise. We'll start with simple questions and we'll bring up an interesting phenomenon of bifurcation. So first, we'll work on L2. On L2, I define the scalar product integral between 0 and 1 of fg. And so I ask you to prove that I will define phi k, some functions of x, phi k, phi l of x equals 0. If k is not equal to L, and phi k equals 1, where phi k of x equals, it's the cosine of k pi x. For k belonging to n star, so and for and phi 0 of x equals 1. All right, so try to prove that. It's a simple computations. All right, so you have this computation. So for k and L positive, you have that so I I will use this trigonometric formula, which says that this is true. So when k is not equal to L, I get that. And this is 0, or all these things are 0 if k if k equals L, and I do not consider 0 here, the same computation leads to this term will be the same, but I will get here. I will get here 1, so it's 1/2. So this gives the result. This gives the result. So yeah, I didn't do the computations for k equals 0. You can do that by yourself. Okay. So we'll stop with that today, and we will continue next week.